Hello and welcome to another one of these ADD videos. Today we're going to be looking at the reaction quotient versus the equilibrium constant. Well, if we were to look at a chemical equation, we could derive something called a mass-action expression, which is the ratio of the concentration of products over the reactants, in which the coefficients of the chemical equations are the exponents of the molar concentrations. So what do I mean by that? Let's take a look at just some random reaction. The mass action expression for this would be the products over the reactants, the ratio, so it would be big C raised to little c, big D raised to little d. And at any point in this reaction, if we plug in these concentrations with the given coefficients, we find what's called the reaction quotient, otherwise Q. Alright? So the reaction quotient is the numerical value of the mass action expression. Alright? So a curious thing happens when no matter what concentrations you use here, the reaction reaches equilibrium at a specific ratio every time. So by definition, the reaction quotient becomes the equilibrium constant, and it always must be that value, that ratio, for it to be at equilibrium at a given temperature. You know that if your reaction quotient is not equal to the known equilibrium constant, then your concentrations aren't giving you equilibrium. So basically, the take-home message is, for any chemical equilibrium to exist in the reaction mixture, the reaction quotient Q must equal Kc. So just a quick side note, you might be asked, given a Q, which way does the reaction proceed in order to reach equilibrium? So if we were to look at a potential energy diagram, and this is the reaction proceeding. So the reaction quotient so as Q reaches equilibrium, there's a minimum in the potential energy, a desired minimum. So basically you can look at it like this. Here is Q, Kc is right there, and here's another value of Q. Alright, so over here Q is less than Kc, and we've got different colors to them. Blue, that's an interesting blue there. Q is less than Kc. So which way would we need to go to get to Kc? We'd need to go downhill to the right, right? So if they ask the question, if Q is less than Kc, we'd look up there, we would need to move the reaction quotient to the right. Okay, so in other words, Q would need to be greater, and we would need to increase product concentration. Alright, and then if Q is greater than Kc as it is over here, we need to go back down and to the left to achieve equilibrium. So you hear the low green roll, East Alice sirens in the background, sorry. You got it. Move to left to reach. So in this case, we're going to increase our reactant concentration. Alright. Again, take home message, Q must equal K to be at equilibrium at a given temperature, and know the directions that you need to go if Q is less than or greater than Kc. Alright. I hope this concept video has helped. Make sure you look at the example videos and also the rules pertaining to what you do when you add elementary processes. For instance, what do you do to their equilibrium constants? Alright? Practice, practice, practice. Thank you and have a nice day.